let's talk about the projection of f onto PQ as a vector, because above we just looked at the distance of it, right? We got the length of the projection of f onto PQ using trigonometry, didn't we? But sometimes if you're working with vectors and you want the projection of f onto PQ as a vector, it's nice to have a formula for computing it. So I'll bet we can come up with a formula for computing it based on partly on some of the work we've already done. So if we redraw that picture, I may not be using the same colors anymore, and that's okay. Okay, so let's call this guy F and this guy PQ. And then notice I don't have PQ at horizontal anymore, but it doesn't matter. If you project F onto PQ, you just project it in a perpendicular fashion. And then the vector from here to here represents the projection vector. And it is a vector. And we think of it as the vector component of f in the direction of PQ. So that's probably worth writing down. So how could we find a and we've already done this kind of. How can we find a representation then using our dot product and our formulas that we've developed for the projection of f onto PQ, a calculation formula? Well, we know the length of it, right? We know, so symbolically, we know that the projection of f onto PQ would be the magnitude of the projection of f onto PQ. That's the length of that vector in green right there. Times a vector that points in the same direction as PQ but is 1 unit long. Remember that trick? So what I'm saying is this. If we could find the unit vector that points in the same direction as PQ and multiply it times the length of the projection of f onto PQ, then we have our vector form of it. So what I'm saying is this. PQ divided by its magnitude, you guys all know that this guy right here in the orange parentheses, that guy is a unit vector, right? In the direction of PQ. This guy out here is the projection of f onto PQ. It's magnitude, its length, right? So if this vector in the parentheses is 1 unit long, and it's in the direction of PQ, and you multiply it by the length of the projection of f onto PQ, that resulting vector is the projection of f onto PQ. So now we should be able to come up with a formula in terms of our vectors, our dot product and whatnot, that we can use to calculate the projection of f onto PQ. So what do we know from above about this length? Using the same idea as above, we know that it's the magnitude of f times the cosine of that angle between them, right? Magnitude of f times the cosine of theta. That's from the ka part of SOHCAHTOA if you think of this guy as a triangle, right? And then we still have the PQ divided by its magnitude. Any questions there? Okay. Then what I'll do is I'll stick in the formula for the cosine of theta. And we'll get to where we want to go. Now you're used to the formula in terms of u and v, u dot v divided by magnitude u, magnitude v, right? So here we're talking about f is acting like u and pq is acting like v. Okay? So the formula for the cosine of theta, we still have this magnitude f here. I'll do the cosine theta in orange. It would be, if I slip and write single magnitude bars, it means the same thing as double magnitude bars. Okay, in fact, your book uses single magnitude bars. So instead of u dot v on top for the cosine, I'll do that in orange. It would be f dot pq divided by magnitude F magnitude PQ. Isn't that the same formula above using different letters for, that, you know, as what we used for the cosine? Everybody believe that? So the stuff in blue didn't change. Everybody with me? There's anything canceling here? Magnitude F. Oh, and then we've got magnitude PQ times itself. So here's what we have. We have F dotted with PQ. I changed this orange to blue. And then I'm going to put the magnitude of PQ squared underneath it. And then on the outside, so this vector is on the outside. Ultimately, since this is a scalar that I circled, it's a scalar, right? Dot product on top, magnitude on the bottom, both numerator and denominator are scalars. So this is a scalar that I circled. It's a scalar times a vector. So remember, when you multiply a scalar times a vector, you get another vector that's parallel to the original. We think of it as parallel. Scalar multiples of vectors as parallel. And really, it just represents this vector in green in the picture. And it's something we can compute. We can use this formula to compute. Now, more generically, then if we want the projection of u onto v, so v is taking over the role of PQ and u is taking over the role of F, what does this formula become? On top, u dot v. What goes on the bottom? What's taking over the role of PQ? V, so it's got to be magnitude of v squared on the bottom times v on the outside, the vector v. So this is your projection formula. It's another one of those, make a flashcard out of it. Left side, projection of u onto v, or left side. One side, projection of u onto v, other side, the formula u dot v divided by magnitude v squared times v. You want to get it memorized.